Okay, we're live. There I am. I see myself. And I'm sure the light's on under the tape. Yeah, there we go. Of course it is. All right. So, hello, welcome back. Thank you for being here. My name is Verite Arbusto. This is the Schumann Resonance channel on Facebook and on YouTube. Schumann Resonance Harmonics. Thank you all for being here. This is part of this video is part of an ongoing series in the magnetic pole reversal, magnetic pole excursion, and possible switch or swap. Okay, so the question is, what would happen to the Schumann resonances if we had a pole shift? And that's the extra super duper extra point, extra credit question. Before I can get to that, to answer that sufficiently, there are other factors that I need to talk about. And the first is, what is the pole shift? What are we talking about? What is the magnetic pole shift? That's a phrase that's been kind of bandied around. There's not a lot of people who kind of have a really good lock on it. And so, from my view, all right. So, anyway, before I can get to the extra credit, I wanted to, lay down some basic information. There's 3 different places that have addressed what this is. And I want to kind of give an overall view of what it is. And then there's also this movie by Suspicious Observers called Cosmic Disaster, I believe it is. So with that cheery title. All right. So, all right. I'm at the, have gone through maybe half of this article, and I'm kind of gonna go over the last chapter, or not chapter, the last paragraph that I had read from last video. I'll kind of pick it up, but from a chapter, a paragraph before where it cut off. All right. So we're talking about the geomagnetic polar reversal. All right. That's the name of this article. All right. So although the conditions that gave rise to the geomagnetic polarity reversals are not completely understood, it is known that the reversal sequence of the Earth's magnetic field contains information about Earth's core processes. In particular, from the analysis of the length distribution of the polarity intervals, it is possible to try to model the reversal mechanism, while from the analysis of the rate of occurrence of these reversals, it is possible to try to gain information on gradually changing conditions at the core mantle boundary. Indeed, it is generally accepted that the changes in the frequency of field reversals reflect the dynamic evolution of the fluid core, and that the analysis of long-term trends in geomagnetic reversal frequency might provide important information on core mantle coupling. Core mantle coupling. All right. Okay. All righty. Okay, let that sink in. Next paragraph. Modern reversal chronologies show more than 300 successful reversals in the past 166 MA, big A, MA. Indeed, it has been found that the direction of the dipole component reverses on an average about every 300,000 to 1 million years. These reversals are very sudden on a geological time scale, about 5,000 years, and the time between reversals is highly variable, sometimes occurring in less than 40,000 years, and at other times remaining steady for as long as 35 million years. No regularities or periodicities have yet been discovered in the pattern of reversals. Indeed, a long interval of one polarity may be followed by a short interval of opposite polarity. All right, so now they're giving you this chart here of the different, lengths of time where it's reversed and normal and all of that. All right. I'm not going to go into it, but you can see it's very varied and has this long ass period of time there, blase, blase. All right. Continuing with the text, a time interval in which the geomagnetic field is predominantly of one polarity is known as a chron. Typical lengths range from the order of 0.1 to 1 MYR, a million years, I guess, with those rare, extremely long intervals dominated by one polarity being designated supercrons. The polarity crons are interrupted at regular intervals by shorter polarity subcrons, originally called events, lasting for 20 to 50 Ka. At times, the polarity record shows large departures of the magnetic pole from normal or reverse polarity, but the polarity does not change completely. The pole wanders into equatorial latitudes but returns to its original location on the rotation axis. The departure is short-lived, lasting less than 10 Ka, and the phenomena is called a magnetic excursion. Okay. So that's what we're talking about here, magnetic excursion. Okay, so I think I have time. I'm going to see how much time I have. I'm going to play some of this, and we'll see what. Let me just play it.
It does not take much research to learn that magnetic reversals on Earth happen hundreds of thousands of years apart. So what is the excursion? How does it differ from a full magnetic reversal? We have been examining the effects of magnetic changes on Earth, potential cataclysms that may arise, but there are those studying another form of great change during these magnetic events, a slower version of extinction, an appearance of new species, and which doesn't require a single short-term catastrophic event. A recent paper in the world's #1 geophysics journal highlights this disaster that looms on the geological horizon, but it's not something that happens hundreds of thousands of years apart.
We call them excursions, magnetic excursions, which is, a term that's well integrated in the literature now. And these are very short-lived reversals, but they're associated with minima in field intensity, and it's the minima in field intensity that are implicated because when you have low field strength, you enhance UVR.
So unlike the full chron events, the full magnetic reversals, these excursions are very short. They happen relatively quickly and return, but they include the dreaded minima of magnetosphere strength. So this begs the question, how often do they occur, and when, oh when, was the last one?
Well, as we head back in time from today, there are a number of very well-documented excursions, magnetic excursions. One is at 40,000 years, which is called the Lechamp excursion. And then as we head further back in time, we have another very well-documented one, which is called the Blake excursion at about 115,000 years ago. And then we have one that's at 190,000 years ago. And then there are a number of other excursions that are not so well documented. And there's one at about 13,000, another one at about 32,000. So there are a bunch of them. The reason why they're difficult to document is that, as I said at the beginning, they have short durations. So it's difficult to record them in geologic archives.
Would it be possible that the Mono Lake or Lake Mungo excursions
have evidence that is there, and because for the reasons you've described, it's just too hard to find, or we haven't found it yet, to call it a more recognizable event?
Yeah, I'm sure that's the case. I mean, although the first magnetic